All right, let us begin. So hello, everybody. Welcome to a CMU Robotics Institute RoboLaunch workshop on control systems intuition. My name is Teodor Tchalakov, a 2022 Robotics Institute Summer Scholar and undergraduate student from the University of Illinois at Urbana-Champaign studying computer engineering. This workshop was designed by Brady, Indu, Panigrahi, and I to guide you through the motivation and intuition for controlling a robotic system using the PID control algorithm. At the end of the workshop, you will get the chance to interact with the ideas covered today through a Google Colab notebook and test your new control skill systems. Let's first start by looking at something you probably have played with before, a remote control car. This particular car example allows you to turn the wheels on the left and right sides separately when you push some joysticks, which then apply power to the motors. This handheld control scheme makes it easy for a human to control the car, as it takes little intuition to make the car turn right, left, go forward, or spin in place. This makes it seem like manually controlling a car is sufficient enough to get it to do anything for you. But what if you wanted the car to drive forward exactly 10 meters? It will be difficult to know for sure that the car moved forward exactly 10 meters. So you might have to mark the ground with chalk and then drive it there, which would be tedious. Likewise, you might also want to get the car into a specific orientation. This clearly raises a new challenge in how accurately you could drive such a car. So how can we solve this problem? Maybe you might consider needing to measure with a sensor exactly the distance and orientation of the car. Then you could probably just twiddle around with the joysticks until the distance you see from the sensors is exactly 10 meters. How about a different system you might be familiar with? A quadcopter drone. This one will not be as easy for you to fly around with just the twiddling of your thumbs. Plus, you might need 4 thumbs and a joystick for each propeller's motor to do so. Compared to cars, quadcopters will require 100% of your attention to fly around, especially when the wind picks up, because cars will start in place regardless of the amount of wind. It just doesn't seem likely that a human will be able to react fast enough to fly a drone by directly controlling the 4 motors. For instance, take a look at this video of a quadcopter stabilizing itself. Would you be fast enough to react like that? So clearly some of the cool things that people can build cannot be easily controlled with a handheld joystick, or might heavily benefit from some sort of assistance. In this case, it would be convenient if you could just tell the quadcopter to move sideways, forwards, and backwards, or up or down. And it would figure out how to spin its propellers to do that while keeping itself hovering and then become level. How about a robot arm with 3 joints and motors that has a gripper at the end? You could again use some joysticks or even buttons for the controllers and painstakingly move them to the desired location to pick up something. But you run into the problem that it would clearly take a long time to adjust each joint. If your arm was not very well built, moving other joints could also make the other joints shift from their previous positions, making it once again inaccurate. It'll be much better if you can move the arm quickly and precisely like a human, as shown in this video. This sort of control will enable you to create an arm that can pick up things quickly and move around regardless of the number of joints, and it should be able to do it very accurately. So the underlying task in these motivating examples is to control something such that it achieves a given goal or task. So let's try to define the idea of control through an example. Say we extend our remote control car example to a real autonomous car with no human in it that is driving in a specific lane and approaching a crosswalk. The goal is to have the car stop exactly at the crosswalk. We do not want the car to overshoot the 10-meter mark and possibly hit a pedestrian, or stop too far behind and not be able to see incoming traffic. To control the car to achieve this task, we want to define its actions such as how much it should be turning its wheels and when it should brake to end up exactly at the crosswalk. This is what control is. We start with the car, which is our system, and we want it to achieve a specific set of goals, and we should define exactly what to do at the crosswalk. And we use rules and logic to control the system, such as when to brake. So as you can see, while a human would be able to intuitively solve most of these problems, it would not be reasonable for us to do it as accurately with a car, or keep track of all the propellers on a drone, or move an arm fast enough like how we do with our own arms. Of course, controlling the speed of autonomous vehicles is only one application in robotics. There's also raising and lowering robot arms for grasping and manipulation, walking robots, and so much more. But control is also used in common settings at home, such as your thermostat with humidity and temperature control, or a refrigerator keeping your food nice and cool, and also for automated kitchen appliances, such as an automatic pressure cooker. But now let's dive into a more detailed example that you'll have the chance to experiment with at the end of this workshop. Consider a simple robotic arm that is made of a gray rod that is anchored in place on one end and allowed to move freely at the other. You can move the arm with a motor at the fixed end of the rod, as it can apply a force called torque to turn it clockwise or counterclockwise by using the joysticks on that controller. However, this motor can only apply force if it doesn't hold, and it does not hold in place the arm once you let go of the joystick. So something could move this arm, such as you moving it manually, or some wind, etc., lots of other disturbances. But one interesting one to consider, for instance, is if we consider gravity, then the arm will attempt to swing down to a resting position pointing downwards. In this case, if the rod is on the right side of this imaginary line, then it would turn clockwise because of gravity pulling it down. And if it was on the left side, it would turn counterclockwise also because of gravity. Once this pendulum arm has slowed down, then it should eventually reach this downwards resting position. So now that we know what we are working with, let's start with our first task, to get the arm to point upwards from wherever it starts, with or without gravity. So let's look and analyze some locations for where the arm could start. If the arm is on the right side, then we would probably want it to turn counterclockwise so you can get there as fast as possible to the upwards goal. And if it was on the left side, we probably want it to turn clockwise. Simple. So then we should really simply just choose a torque for turning it counterclockwise and clockwise and just apply that based on which side it's on. Great, that's our controller. That should be really simple. So let's actually describe how this controller would look more mathematically, because at the end of the day, we need to take it and put it on a computer, and that computer will run that control algorithm. To do that, we'll be using degrees to describe the location of the pendulum. So in this case, we're going to be using 0 degrees as straight up, and everything clockwise is going to be positive, and it will wrap around and continue each time that you continue to go around the circle. Likewise, counterclockwise will be in the negative degrees direction from the upwards position, and it will also continue to wrap around. So you can imagine that if you wanted the pendulum to do 2 full clockwise turns, you would need it to go from 0 to 180 and then back up to 360, and then again continue until it goes to 720 degrees in that same direction. With that description, we can build our Bang Bang controller, which is the general name of a controller that is the simplest form of controller that we will now lay out the framework for. So first off, we need to talk about our goal. Our goal, also known as a set point, is to just get the the pendulum to be at 0 degrees. So then we know that once it's at 0 degrees, we don't want it to do anything. We want it to stay there. So we'll make that the first rule. The second rule is if it's on any of the positive degrees, then it should be moving in the counterclockwise direction. And if it's in any of the negative degrees, it should be moving in the clockwise direction. Then we'll also want to choose how much torque we want the motor to be applying, just so we can decide how quickly or slowly it attempts to go for this set point of 0 degrees. So congratulations, you have just seen and come up with your first control algorithm in the most simplest manner possible, just trying to choose the correct direction and get to your goal as fast as possible. So let's see how it performs. As we can see, if the Bang Bang controller was the correct choice for our system, then we would hope that it would slow itself as it gets towards its goal and eventually reaches it. However, if we put this controller on a different arm or maybe make its torque larger, you would notice that it most likely is going to be very aggressive. The controller keeps on overshooting and then having to correct. However, this doesn't mean that the controller would not be useful. It is a very simple controller, and all it requires is that your system has a lot of resistance and can slow down the controller once it gets near the goal. So if it doesn't, then how can we slow down the control when we get near the goal? We now know that our goal is to describe the amount of control that we are applying to the motor based on where the controller is. But first, we must give an exact definition for how much we are going to push the motors. To do this, we will use the variable u to describe how much and in which direction we are applying force or torque to the arm. A positive u will turn the arm in the positive degree direction, and a negative u will turn the arm in the opposite direction. So we'll want the value of u to be negative when the degree is positive, and for u to be positive when the degree is negative. And likewise, we'd want u to be 0 once it is at our target. So the best function to do that will probably be just a straight up u is equal to negative theta, following the rules that if we're on the positive side, we want to be going in the negative direction. If we're on the negative side, we want to be going in the positive direction. However, we would also want to control, once again, how strong the relationship between theta and u is in order to define how much the arm should be pushing itself when, depending on how far away it is. To do this, we'll just multiply our value of theta by p, and this stands for proportional. And so now we get our P controller. Now let's see what this looks like. Wow, could you believe that? The controller goes to its set point quickly and without any massive overshooting. Now, this is assuming that it is a exact system that you understand well and that you have chosen a correct p-value. But the important thing to note here is that when the torque goes to 0, it stays at it. It has reached its goal and it's staying at 0 torque, so it's not going to move away. And if it does, it'll just once again try to bring itself back. However, what if we didn't choose a very good p-value? If the p-value is too large, the controller would be pushing the arm really hard towards the target angle, and as it builds up speed, it will most likely overshoot. But once it overshoots, it starts pushing it in the opposite direction, but it takes time for it to change its direction, so the controller is going to go back to the same position as it was before, but the result is that it will get possibly stuck oscillating. However, if the p-value is too small and there's gravity, some sort of disturbance in your system, then the controller might not work hard enough to lift the pendulum all the way to the goal, and so it may never reach its goal. Isn't it surprising how important it is to choose a correct p-value? The best way for you to choose your p-value is through experience tuning the systems and recognizing the behavior of p-values that are too small and too large. So in this case, if the pendulum doesn't reach the target, then you should increase the p-value. And if it begins to overshoot and even oscillate, then you should decrease it. But the good thing is you'll have a chance to get some of that practice today with the interactive. However, tuning a p-value could take a while in order to solve the problem. Also, you would need a system that is, fit for a p-value, and there are many ways to figure that out. But what we'll want to solve today is the problem of overshooting and oscillation. So let's take a close look at the pendulum and see if anything could be done to fix this. What we have noticed is that large speed typically causes overshooting and also oscillation. So what if we decided to penalize the velocity when it gets large? I would like to introduce the PID control algorithm, where again, our goal is 0 and we have a P controller, but we want it to, in a similar fashion, penalize the velocity V and then once again scaled it. This would mean that if the controller is moving in the negative direction, its speed is going to be, it's going to be a number that isn't 0 and its velocity will be negative. So we will try to use this to decrease the control in that direction, and therefore the control will be much lower than what it would be if it was just a P controller. Likewise, in the positive direction, we want to decrease the control that is positive. So let's take a look at how adding a P controller will affect, adding a D to our P controller will add more stability or help out with getting us to the target point. So once again, if we didn't have a D to penalize the velocity, then we'll get this sort of oscillating pattern. But on the other hand, once we add a D value, we penalize the velocity, we'll see that a good D value will make the arm start to slow down and therefore actually reach its goal. On the other hand, a large D value will make the controller really try to slow down. But I would like to note that if you choose a very, very large D value, then if you accidentally measure and your arm or car or anything, and you see that it has a very small amount of velocity, even though it's not moving, the large D value will amplify that. And suddenly it will tell your system to start moving, even though it wasn't moving in the first place. And it shouldn't be moving. Now, if the D value was too small or insufficient, then it would just become a P controller again, or it would take a very long time for the controller to slow down its oscillations. So remember back to the P controller, there was still another problem we had to solve, which is when we have an arm that has gravity, and so it's basically a pendulum, and the controller can get stuck. So we call this steady state error, which is when the controller gets stuck at a specific location, and so that the error between where it is and where it wants to be stays the same over time. So let's talk about an example that illustrates this. Let's say we had a P controller where P is 1 and theta is 90. So our U is going to be 1 times 90, which will give us 90. Now imagine if gravity was also providing 90 torque. The result would be that these torques would cancel out and our control would just be nothing at that point. This can be dangerous if the system doesn't have any speed at that point in order to get away from the point where the control results in nothing happening there. And so you can see here that it can get stuck in that location. So to solve this, we want the controller to realize that it's being stuck in place. So I want to motivate it by having it think about going towards its goal and to pressure it to go towards its goal when it's not at its goal. An example of this is like thinking of when you have a homework assignment or project due in a couple of weeks. When you first get your assignment, you won't need to work on it as much. So there's not as much motivation to there's not as much motivation to get it done. But as the days go on, then you start to feel more pressure to get it done. And so this motivates you to finish your assignment. We will use this to create the PID control algorithm, where again, our goal is 0 degrees and we have our previous PD controller, but with an extra accumulated error concept to pressure the controller to go to its goal and a scaling value I to describe how strong this effect is. So what is accumulated error? In our case, accumulated error is the sum of how far away the arm is from the goal at every time that we measure it, and then we just add this up. So for instance, at 1 second, we will see that the arm is at 90 degrees, so our accumulated error is 90. Then at the next second, it is still at 90, even though we applied a PD control, so the total accumulated error will be 180. But now this accumulated error has grown and there's more pressure. And so it's going to start pushing the controller. And we can see at 3 seconds, it goes to 80 degrees. Then we measure that again and we add that. So we have 260 accumulated error and so on. However, when using accumulated error, try to keep in mind what will happen if the error keeps on growing. And maybe even try to figure out strategies for how to stop it from getting too big. I'll leave this question to you to play around with and think about while you're doing the interactive at the end. Now we should try and see our final controller working. Once again, if we do not have an eye in the controller for an arm with gravity, so pendulum-like, then the arm will get stuck. But if we add eye, we can motivate it to get past this stuck point and go towards the goal that it has at 0 degrees. But notice how as it gets past about 10 seconds, it overshoots because the accumulated error is still on the positive end. And now when it gets to the negative end, it wants to stay in the negative end until the accumulated error gets to 0. On the other hand, if I is too large, then there is too much pressure and our pendulum will start to oscillate and, well, go crazy. And if our I is too small, then it will take a long time for the error to accumulate. And now the accumulated error will be super high, which might cause problems if the accumulated error does not decrease. So what other problems are there? In PID, there are a lot more things that go into creating the PID controller, and it takes a lot of understanding of your system to tune them properly. And even if you did know your system, there are methods to figure out exactly what PID values are best for your application and problem. And I and D also have their own problems when you actually go and implement them on a system themselves. But that's just PID. Control isn't just PID. There are so many other interesting things that you will encounter in control. So here are some of them. First one is controllability. This is the study of whether or not there is a way to control a system. Another one is stability. Is there a way to get the system to stay in place and not deviate from some sort of local point? Likewise, the one that a lot of people care about is optimality. Is there a best solution in terms of maybe time or how much power the motor is using? Then there are some other ones that should also be kept into account because you don't want bad behaving controllers, even if they will achieve something for you. And so those are feasibility. Is the question of, would it be even reasonable to implement this? If the controller was super slow and it was updating every 10 seconds, then it wouldn't be a good controller. Likewise, reachability. Left alone for to have the controller move on its own, where will this controller go? And paired with that is safety. Where will a controller go, and will it always behave in a safe manner if it is allowed to go wherever it likes? So now we'll be moving on to the interactive part, but first, if there are any questions in the webinar or on YouTube, I will be happy to take them, or in the room as well.
So when you're using those controllers and looking at accumulated error, are you using discrete points, or are you taking limits to like take small fractions to add like the error? If you add it every 1 degree, you add more error, or how does that work?
So typically a PID controller will be implemented on a discrete time system. And so every single time that you measure it, it's, if it's a continuous, if it's evenly spaced out measurements, then every time you measure it, you just add up the accumulated error. And one thing that is interesting about how the I is done with is because it's really just an integral, and the integral will be scaled by how much that time interval is. So if your time interval was even, then you just take that out and change the scaling value of the I that you have in front. But otherwise, you could also just, every single time that you measure the interval, and then you take that and you find the integral for that time step and just approximate it. And so that's how you would accumulate error over time when you're implementing the controller on something that is, discrete. And PID controllers are very fast, so they'll actually run about 1,000 hertz, very fast.
Thank you.
Is it worth it to just like have a quote unquote perfect p-value versus doing the whole PID thing?
Can we answer that?
Yes, I will give a little motivation for thinking about it. So for everyone online, the question is how important is it to find a perfectly tuned p-value? Like it might seem like you don't need the I or the D components to add to control your system, but the p-value, that's the first one you need. And the question then becomes, well, you have to understand the question becomes, how well do you understand your system? If your system was damped in the sense that it will dissipate the energy that it has, or it will slow down by itself, then just a p-value is enough. But if it didn't do that, then you would get the behavior of oscillating, and so the D value is going to need to be added so that we can penalize that. But there's an interesting interplay between the P, I, and D controllers, and there are different ways to implement all of them. More specifically, how to implement the I and the D controllers. The P one is the simplest. And really choosing how to tune them is dependent on your system and your application and what goal you have in mind for when you want to make your controller. Any other questions in here?
So with just a P controller, could you get past the steady state error?
So with the pendulum that has, so in the pendulum case, so yeah, with the pendulum that is in this sort of 90-degree angle, as long as the total torque that from gravity is less than the torque that you're applying from the controller, then it will fly past it and get there. But in general, the other thing that kind of defines steady state is the fact that, in this case, we did it with just gravity, which is constant. But another case in which it would be nice to have an I value to help you get out of a steady state is like, you built your system to, withstand this, and that. And then you tune the values based on that. But let's say there's like wind now. And if you had wind, then an I value that is pushing the controller to the side from the upwards position would help you deal with that disturbance in a, in a more sort of controlled way than if you had to go back and then increase the p-value to account for that wind, because the wind can be variable. Okay, well, I'll pass it on to Brady, who will be taking you all through the Colab session.
Okay, thank you. So yeah, if everyone can pull out your laptops and pull up a tab, and Daniel, if you could take this URL and copy it into the YouTube chat and Zoom chat, that'd be great, because then I can move on from this. If you're watching online, I'd recommend maybe doing a split screen if you can, or just have an easy way to flip between these. So if everyone can get that, then I'm going to now pull up my own copy. Okay, so what we're going to do, as Teodor said, is we're going to now go through essentially the same process, and we're going to build our own PID controllers on this. Again, this similar experience with on. Oh, yeah, you guys want to see it too. Let me switch this. Here's why. Okay, so first off, what we're going to be using for this is called a Google Colab, and all it is, it's a nice way that you can look at code, you can look at text all on one nice big sheet, and you can run the code online in browser. Yes.
If we run the code here, is it our code or is it?
It is yours. You can make a copy though yourself if you want, just to save it in your drive. If you go up to File, Save Copy and Drive. But if you mess around with this, it's not like it's going to mess up ours or anything. So feel free to type and run stuff yourself. But you could.
If you want to save it, do make a copy to your drive.
Yeah, if you want to save it for later. Otherwise, it will not save your changes. So how this works is in Google Colab, you have these cells, which you can see I can click on each of these cells. See how some of them have text and some of them have code. And so this one right here, if everyone could click on this one, this is called like your hello world, which is like your first code you can run in every language. We're gonna be coding in Python, by the way. And there are lots of ways you can run a code cell. You can do like command enter or shift enter, or the easiest way is there's a play button. And so you can see I can click on that and it should run. Oh, also the first time you run a cell, it might give you a warning saying like, you did not write this code yourself. Do you accept? You can see here it says hello world. Okay, now for our system that we're going to be doing is, again, we're going to be doing like Teodor's example of this arm. For most of this example, we're going to imagine like if we're looking down on the arm, like if you laid a clock on the table and we're looking at it. So we're just kind of going to ignore gravity in that case. So we can just be our simple system. Again, the angles are going to be defined like Teodor said before, except we're going to be using radians just to make our math a little simpler. And again, there's like a motor at the center, which can apply some rotational force, which we call torque, and that will get it to spin clockwise or counterclockwise. Okay, the next thing you'll see here is I have this cell, and you can see it says 7 cells hidden. And you can go ahead and just click the play button on that. All this is doing is it's just importing a bunch of libraries that we want to use, some functions that I made that will print things out and make nice, pretty graphs, just a lot of background stuff that you can look at later if you want by just unhiding those cells.
Should we run them?
Yep, go ahead and click the play button and run them. And yeah, you won't see any output this time. It's just going to run them and save all that for us to use later. Okay. Once you've done that, you'll see your first big block of code. What we're doing here is we're defining what is this robot arm. So there's a lot of properties of it, such as like the length of the arm, the mass of the arm. As Teodor said, like the damping or like that's like the friction force in it. We can set that. What I'd recommend for just our first time through is leave these the same, because you can see you could adjust these with these sliders. We're going to leave them as mass of 1, length of 1, damping 0.1, and you can see we have gravity turned off right now. So go ahead and run that by clicking the play button, and you should see when you run it, there's a little check mark that says you did it. You have a question? Yeah.
If I already messed with those bars, there was like the default.
Yeah, so you can go over in the code, and that's probably the easiest way. Oh yeah, there's no default, I guess, but you can just put in a 1 because sometimes the slider is a little hard to like get exactly on there. You can just go over here and you can delete type 1 and then click play again. So anytime you change a parameter, this is a good reminder too, is every time we change a parameter, you'll have to rerun the cell in order for it to essentially like save. And yeah, as I said, if you look at this code here, it just has the properties, then it has some functions that we will be using. And these do nice things for us, such as simulating the arm moving forward. We can input a torque and it will simulate and say, where is the arm going to be after a time step based on what the torque is that you put in. Okay, now we'll scroll down together and we're now in the section that says, let's move the arm around. So what we're gonna get to do is before we build a controller, we're gonna try moving the arm ourselves just to see what it's like, maybe see what the effects are with the amount of torque we put in. And so what we have here is in this cell, if you run it, you're gonna see a slider that pops up. And what this slider is gonna do is it's gonna save as you slide it around a torque. So if you go to the right, it's gonna be a positive torque, and a positive torque will do a clockwise rotation, and then a negative torque will do a negative or a counterclockwise rotation. And go ahead and click on it and slide it around for about 10 seconds. So what we're gonna use. So you can see I went negative, I'm gonna go positive, and then I'll just like go back and forth just for fun. And you can do up to 10 seconds because we're just gonna run the sim for 10 seconds. So once everyone does that, and you should see a graph of what your input is. You see mine just kind of jumps around. Is that working for everyone? Okay. And now we get to simulate and see what happens. So what this code block does is again, just has a lot of parameters of things such as like, when do we want to end the simulation? Where are we starting the arm at? And then you'll see down here, the most important part, which is this for loop, which all this is doing is looping over time and saying, okay, what was my torque at this time, which we put in input. And then it says, now go try to move the arm with that torque. And so you can go ahead and click play on that. And this will take about like 8 seconds to run because it's going to make a nice animation for you. That should pop up. So let that run. Let it pop out. Okay. And if yours doesn't autoplay, just click the play button. And you should see something like this. See it swinging around. And so what you see is the animation of it. This one in the middle plots what the arm angle was. It does clip at positive pi, negative pi in this case. And then it shows your torque again, what you put in for 10 seconds. So if you want, you can go back and try again, try some other different input. So in order to put a new input, run the cell again with the custom torque, clear what you did, and you can go and try again. So I'll let you take a second to try something else. See how fast you can get it going. One more time. Take like 10 seconds.
Oh, I changed the one up top, right?
Mhm.
And then again, but gosh,
Doesn't look different or,
no, it just gave me an error.
oh, okay. Indu will come in. Yeah.
That's why. So I think this, and I leave in the code, like I'm supposed to.
Okay, that was mine this time.
Oh, okay.
Okay, so now what we're going to do is rather than just kind of messing around with this, we're now going to try to get the arm to do something specific. And what we're going to try to get it to do is now what we're going to also have the controller try to do. So it's kind of like we're going to go head to head against our controller and see which one can do better. So what we want to get the arm to do is what this little GIF shows. So we're wanting it to go to the right, hold for 5 seconds, and then we want it to go to the left and hold for 5 seconds. And obviously that's impossible. We can't just like teleport there, right? But we're going to try to get there as quickly as possible and then get it to stop and go as quickly as possible and get it to stop. And you can scroll down. I have new code blocks for this that will also then plot your goals. So you can again run this code block, which does your custom input, and see if you can get it to do that, where it goes to 1 radian, holds 5 seconds, and goes back. So I'll give you a couple minutes to give that a try, give it your best attempt that we can then go later and we'll kind of compare them at the end. Oh, and one point I want to say too is over here, you can see there's a box that says animate sim. You can turn that off and then you'll see that I get results extremely fast, but it doesn't create the animation. But that allows you to do a bunch of tries really quickly and you'll just see the plots. So you can choose to turn on or off. If you have a lot of patience, you can keep the sim on every time. Okay, good. Okay, everyone had a chance to try it? Okay. Now we're gonna move into building our controller. So the first thing we're gonna do is, again, starting with P. So as Teodor said, the P is like our proportional controller. And we're gonna write our controller in this function down here, and you can see it's called P controller. And we're gonna pass in 3 variables with P, which is something that we get to pick later on and we'll mess around with. There's the goal position, which in Teodor's, it was always 0. In this case, we're gonna make this a function that you can put in any angle you want, and it's gonna try to get there. And then the current position. And then the first step we do in this function is we take the goal and we subtract the current position, and we would define that as the error between the two, right? So we set that as this error variable. And then we now need to pick what should u be. So in this case, what we wanna do is we wanna take the error and we wanna multiply it by P. And that's essentially gonna scale this error, and then we're gonna set that as our input, as our torque. So I'll give you a chance there to write in. So you can see where it says add your code here. So after the U, and you want to do your error times P. So I'll give you a second. Oh, and yeah, if you haven't coded before, multiply is the asterisk sign. And once you have that in there, you'll need to run that cell so that we can use it later. Again, look for that green check mark saying that it all worked. Okay. And then, so now this code block is just like the sim block before, but now rather than the torque being your custom one that you threw in, it's now going to run this P controller. So you can see at every step of this loop, it's going to pass in the P, which we get to pick over here. And then it's going to take what is the goal, where are we trying to go, which is that square wave thing. And then it's going to take where are we right now. So I would recommend first just give it a run with the default P and see what your results are. So you can see this is probably much better than what you had before. At least you can see it's trying to get up to the 1. And then once it's there, it needs to now get down to -1. So it starts to go down to -1. So I'll give you a minute to mess around with P, to change it, run the cell again, and see how good of a result you can get. So try going maybe big, try going small, and see what kind of results you can get there. And if you have any questions, feel free to say now. Okay, so now we're going to look at a couple things with this. You may have noticed I added this parameter period, which is how often a square wave goes up and down. So I'm going to look at a couple of things of how P affects this. I'm going to increase the end of our simulation and increase the period time so that you can see here, it essentially just creates a flat line. So we see with this low P value that we go up, we have a little bit of overshoot, and then it does settle to where we want it to be. And we can try maxing this out at 5. And you'll see that it's actually very unstable. You can see the angle actually gets larger and larger and larger because as it overshoots, it's gaining so much speed, and then it has to come back, and it has to, again, it just keeps building up all this speed. But if you go down to the very smallest value, oops, I just closed that. You can see, oh, look, it doesn't overshoot, but look at how long it takes to get there. So in this case, it takes about 30 seconds for it to settle. And if you think about the robot arms that you would maybe want to interface with in your life, you probably don't want it to take 30 seconds when you say, go to this angle, and it'll take there, and it takes its time, but it does get there, right? So this is what leads into why we need to now maybe upgrade this to the next step. So now what we're going to do is add in the D of our PD controller. So if you scroll down, we have this function PD controller. Looks very similar to before, but we now are going to also pass in a D. We're going to pass in the current velocity. And the first part of this control equation is going to be the same as before. So we go error times P. But then if you remember what Teodor said, the way that we're doing this with the D is we want to have it slow down when it's going too quickly. We want to discount or dampen the system. So what we're going to do is we're going to subtract, and we're going to take the current velocity. And then we're going to multiply that by D. So when you look at this equation, you see the first part is the same as before. When we're really far away, we're going to have a big error, multiplied by P. That's going to try to get us back to where we want to go. But we say, hey, look, when the current velocity starts to get too big, let's maybe slow things down a bit. Let's subtract off what we're inputting into the system. So we're gonna give you a second to get that there. Once you have that written, you wanna click run. Also, as a side note, if you want to double check what you have, you can double click on the cell below and it does open up right there. And you can use that. Okay, so once everyone has that equation, we're gonna go down to the next part and we're gonna run this. So you can see the P is gonna go reset back to something before. But kind of mess around with these values, the P and D, and see what kind of effects you get on the system. Again, I turned off the animate sim just so that it goes faster for you. So you can give that a run. So you may have noticed a couple things from this. So one is if we just look at the D value and hold that constant. So let's say I just set D to 0. We get this kind of effect. Again, we get these massive oscillations. And if I put D all the way up, you can see that we've now offset that and we've now made it so that it doesn't even get to the 1 anymore, which is worse than before, right? So we're essentially saying just don't go fast at all, slow yourself down, just creep all the way to the goal position. So now what I want you to do is play with both of these and see how good of a response you get. So one thing we've added, if you look above your graphs, you can see there's this line right here. And it says user, anonymous user, and a number, and this is total error. That total error is telling you accumulated across the 10 seconds, how much error you have. And I want you to see how low you can get that. And you also notice too that you have a anonymous username. And I've actually have where you can compare and kind of see what are some of the results other people are getting. So, and you can go ahead and even change your name if you want. Up here, it says the anonymous user. You can change that to your name if you want. And I'll have this up, but you can see this updates with all of your submissions and see how low you can get with that error. So I'll give you a couple of minutes to try that. And this will show us kind of what is the minimum that we could get with this system. So it looks like right now the lowest we're getting is about 1.26 or 27 if you're around.
Save some of the rest of this.
Okay, so it looks like we're all getting pretty good results here. I'll give a couple. I'll give maybe a minute more if everyone wants to mess around a little bit more. It's fun to see everyone's kind of collectively just accumulating down here.
It should be doing error and number of tries.
Number of tries. You only get one try, just guess.
Okay, let's go. Bro, can you chill?
Yeah.
Relax. Are you 2837? Are you 2837? I'm 1.4. The Scala is coming here and everything. I'm like, whoa.
So yeah, if you want to know who you are, you look right here and it says user. See how mine is user 9397, but you can also, if you change your name here, then it will update on there. Otherwise, if you want to stay anonymous, you can just look at what your username is on your own. Yeah. Okay, we'll just give it a couple more seconds before we move on. All right, so I guess we'll move on, but this will stay open, by the way. So if you really want, you could go and see if you can beat the #1 score. I think it was 1.25, pretty much flat. So that's the one to beat. But something interesting we'll look at here. So I'm gonna just give one guess and we'll see what I can get. We'll go with like this, because something interesting that we see Well, actually, I kind of want to go, let's see. So I want to show something, which is, okay, here we go, 1.255. So one thing that's interesting that you'll see is sometimes this error, as we reduce it, it actually leads to a little bit of overshoot. And that's an interesting question to look at is error always what we're going for, right? Sometimes when we're trying to get a controller and we're tuning this controller, it's not about getting there just as fast as possible. And even if we overshoot and we're like going crazy and the torques on our motors are just maxing out, sometimes we also want smoothness, right? So I just want to like bring that up as something to think about, that error is not always just the only goal. Sometimes smoothness or limits of our system are something that we also have to take into account. So in this case, we were going for error, but there are other things to take into account here. Okay, so now that you've built your awesome controller and it's able to get through these angles really quickly, we're now going to test it on your own input. So rather than doing this just boring square wave, we're going to allow you to actually input your own trajectory for the arm to follow. So if you go down to this block right here, so this is under the section test your final controller. You'll see when you play this block, it's going to look just like before with the torque, but don't be deceived. This is now going to be the trajectory for your arm, for the angle of your arm. So go ahead and again, do like 10 seconds. And so I could say like, I want the arm to go all the way up to pi radians, and then we'll go down to, I'm going to max it up to negative all the way, and then we'll go back to the center, let's say. So I can do something like that. And then down in this block right here, you'll want to copy over what your P and D values were above. So if I do something like that. And then I did turn on animations here because it is a fun result to see, but you can, again, turn off if you want. This will take about 10 seconds to run. Animate the plot too. That one takes, you can also turn on animating plots, which is fun. And so you can see here, it actually does pretty well, like following where it's supposed to go. You can see it's trying to follow where we want it to go the entire time. And it gets there pretty quickly without too much overshoot. And we can also run this, just, you can turn on animating plots if you want to, but so I'll give you maybe a second or two to, okay. I think that might've been old actually. Yep. Give you a second to try that out. How'd your controllers do? Is that good? No? All right, yeah, so you can turn on the plots too, and then it kind of syncs up and you can see what the angle of your arm is as it goes. It's kind of fun. And you feel free to save up these videos and share them with family and friends and show off your awesome arm controller. Yeah. Okay. So one thing too that you can look at is, I want you to look at this torque on the right and see what, at the end of the day, what the controller output. So it was saying this is what the arm should be doing. So it's going flat, 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 and then it said, hurry, do 10, then come back to negative. And when you think, would you have been able to do that at the very beginning with your little slider? So that one thing to highlight here is just how impactful these controllers are. They're able to do things that we ourselves could not do. They're able to do it faster. As Teodor said, some of these are running at like 1,000 hertz. So 1,000 times every second, they're evaluating what should my torque be, which is way faster than we ourselves could do. They're able to do like flips and all sorts of crazy things and handle like 20 different inputs, right? It can have a bunch of different rotors at the same time. These controllers are really amazing with the results that they have, and they're able to do it when we ourselves are not there. So you can have tons of controllers and you don't have to have a human operating all of these things. So this essentially wraps things up, but I did leave a portion for you that if you want, you can kind of continue this. You'll notice we did not add the integrator for the PID, the I of that, but you can do that later. And I have some questions that you can think about. So I have down here a controller with the I in there, and then I have a sim loop with a lot of the parameters exposed. So things you can mess around with different goals, goal trajectories. You can change the P, I, and D. I also allow where you can turn on torque limits, because one thing you'll notice too with these torques is that they go extremely high. And in realistic world, motors don't just have unlimited torque that they can do. They actually have a limit. So you would want your controller to cap out at some point so you don't burn up your motors. And so you can go and do that yourself. You can turn on the torque limit here and you can set what that value is and see how that affects the performance of your controller. Some other things you can go and try is you go back to the beginning, you can change the parameters of your arm. You can make it heavier, you can make it longer and see how does that affect your controller? You can go and turn on gravity, and that would make it more like an inverted pendulum problem. And you can try to get your controller to maybe do these same things and have similar performance as before. Yeah, and you can change things such as the square wave amplitude of it. But that pretty much wraps it up. Are there any final questions?
Is the video that Teodor is gonna be up? I wanna watch it.
Yes, these recordings will be up.
Thank you.
Yep. One thing too, if you have a second, you can go, there's a Google form here. So this last sentence right here, there's a link. It's just a 1-question form that gives us feedback on this, and it allows us to see how effective this was in covering intro to control. So it's just the question of what is the muddiest point? So it's like a question you still have at the end of this entire presentation. And if you're watching online, you can go ahead and do that too. Or if you're on YouTube, you could put in the comments any questions you have, and we will try to answer them too. Yeah, we have a
Yeah,
question
we have
now.
a question from YouTube. So is it important to learn about under-actuated robotics?
Yeah, like those are interesting questions. Like if you're going into under-actuated robotics.
Play the video with the triple inverted pendulum.
Oh yeah, I don't think I have that.
Okay,
But that is a good example. On Teodor's very last slide, he had the example of this inverted pendulum, but you can see it had 3 links on it. And so he was trying to balance that, which is very tricky because it doesn't actually have control over all the joints. And so it just is balancing this crazy like chain essentially. And that's a good example. So it depends, but some systems are just very similar or simple, and you can get away with just the P controller or PD. And that's just one of the important questions too, is figuring out what do you actually need, because you don't want to go overkill on your systems. But like this area of controls, and it's a whole area of research, and there are amazing things out there. You can go look at like Boston Dynamics with their humanoid robots that can do backflips and all these crazy things. That's controls and motion planning, and they're all very related fields. Yeah, you can check them out. Any other questions before we close? Okay. Well, thank you guys for your time. Hope you learned something. Hope you had fun. Feel free to keep exploring and messing around with this. Thanks.